Så, hörs något? I'm Nicklas. I'm going to talk about efficient energy storage briefly. So we start with the battery. A battery is the most common electrical energy storage device, and for electric vehicles, the lithium-ion technology is the most used. This technology is based on electrochemical energy storage, which for lithium-ion batteries means that when we are charging the battery cell, the lithium ions moves from one electrode to the other, creating a compound with higher energy in its bound. When we then are discharging the battery cell, the lithium ion moves in opposite direction and we release the energy. That's a simple version of this. In these chemical reactions we can store a lot of energy, which gives us high energy density in the battery. We can store a lot of energy in it. But unfortunately these reactions are pretty slow, so we get low power density and low pulse efficiency. This means that it takes a long time to charge and discharge the battery, and if we try to do it quickly, a lot of the energy goes to heat. Another aspect is the limited lifetime of battery technologies. A lithium-ion battery have a lifetime about a couple of thousand cycles, which is a lot compared to other battery technologies, but it's adversely affected by stress, so such as peak power pulses and fast charging dramatically lower the lifetime of the battery. If we look at another electrical energy storage device, which is the supercapacitors, have the total opposite characteristics. This one is based on electrostatic energy storage, which means in this case that when the capacitor is discharged, the ions can move freely and randomly distributed in the electrolyte. But when we apply a voltage and start charge the capacitor, the ions move to the surface of the electrode and creating small charge separations. The energy is stored in these small charge separations. But the amount of energy that we can store is dependent on the easy accessible surface. And this results in pretty low energy density. But the charge separations are really, really quick, so we get high power density and high pulse efficiency. When it comes to lifetime, so these charge separations are fully reversible. We have no chemical reactions whatsoever in this cell, so the lifetime is about 1 million charge cycles, roughly 1,000 times higher than battery technologies. The fun part comes when we want to combine these things. If we combine lithium-ion batteries with supercapacitors, we can let the supercapacitor handle the peak power demands, and we can lower the stress on the battery. This will increase the lifetime of the battery. We also get improved energy efficiency because of this higher pulse power efficiency, which also enables a highly efficient regenerative braking. So by combining these two different energy storage devices, we can get extended driving range with about 20% and a longer battery lifetime, up to 50% longer. So why isn't this used in the vehicles today? I mean, this is perfect. But we have some limitations because most of the car manufacturers today are using high voltage systems, like Tesla, for example. Around 400 volts, which means that we have 96 lithium-ion cells in series. And for this Tesla schematic, we have 74 cells in parallel. This sums up to over 7,000 lithium-ion cells in one battery pack. This of course need advanced cell balancing, so we don't overcharge the battery cells. We need pretty complex wiring. We don't want to have over 400 volts near us in the car. And also of course heavy insulation. And if we want to combine this battery pack with supercapacitors, we need more than 150 supercapacitors in series to reach this voltage. And supercapacitors can handle high power, so to balance these ones out we need high power balancing. And for 150 supercapacitors this is too expensive. It's not worth it in the car. They are expensive enough already. But if we try to move away from the low voltage system and look at a system with 50 volts, here we have the same amount of cells, but we have 12 lithium-ion cells in series and we have 592 cells in parallel. This gives us much less cell balancing, lower voltage, much simpler insulation, and this also enables the combination with supercapacitors, because here we need less than 20 supercapacitors in series, which means fewer units, less need for high power balancing, and this is really cost efficient. So to demonstrate the use of supercapacitors when it comes to regenerative braking, we made a supercapacitor curse demonstrator, where curse is short for kinetic energy recovery system. This demonstrator have a supercapacitor module of 56 volts and 150 farad, a controller from Sevcon, a 30 kilowatt PMAC electric motor, and uses no batteries, just a supercapacitor as energy storage. It's mounted on a Mitsubishi diesel engine, as you can see here, and this is to analyze possible fuel savings in real-life driving with regenerative braking. So we tested this demonstrator in an accredited engine test facility, and with the standard European driving cycle for urban traffic. In this cycle we have 12% theoretical fuel savings with engaged engine braking, which is a mode that is most similar to normal driving, like normal driving behavior. We could measure 8% fuel savings with this system on, which gives us a good system efficiency. But even more fuel savings can be achieved, because without engine braking, with a modified driving behavior, you put your foot on the clutch when the car slows down, so the regular motor can go down on idle. Then we can save up to 25% of the fuel. But this really needs efficient power electronics like converters. Ken will talk more about this later. So we can use the full voltage range of the supercapacitor device, and we also need highly efficient low voltage motors to make this possible. To round up this part of the presentation, I want to say a few words about the ongoing research on the university today. We have research on low-cost supercapacitors, where we're trying to make supercapacitors that are paper-based and environmentally friendly. And the goal for this supercapacitor is to have the same performance as commercial cells, but to a 90% material cost reduction. And we have, today they look like this, A4 size, this size. And we have about 50% of the performance as commercial cells today, to a 90% material cost reduction. So we are moving forward. So thank you. I will leave the word to Kent.